Hello, everybody. Okay. Let me switch to, no, that's not the right one. Okay, that's probably the right one. There we go. All righty. So can you all hear me? Excelente. Aditya, good. Excellent. Richard, good. Wow, let's see. Pauline, the only person who isn't here is Kenya. And she said she would be there. Dan, good to see you. Carla, good to see you. Kai, excellent. Calvin, Ivy, Lily, Pauline, and Leslie. Good to sort of see you. So I got to share my screen. Right? My computer's going to thrash for a minute, I think. There we go. Oh, puppy. I saw a puppy. Puppy alert. Hello, puppy. Hello. Oh my gosh, what breed is he? He's so cute. Pauline, what breed?
Yeah. I'm not sure.
He's a...
Is he a mutt?
No.
Inu, something.
It's Shiba Inu.
Shiba Inu.
Oh my goodness. He has a fancy name. You know the Shiba Inu, Pauline?
Sorry, say that again, Dr. T?
You know that type of dog?
Yes.
You do? Did we pronounce it right?
Yes.
Okay. All right. So, you guys want torture now? Everybody
No.
say yes. Everybody say yes.
Depends upon what torture is.
Depends on the torture? Oh, come on.
I don't want to be tortured.
I'm a creative guy. I'm a creative guy. So the worst torture I can give you is just being as boring as I was last time. And sometimes you actually like that because if you're like Kai,
Please take him away.
Something completely different the whole time, and you don't even listen because when I call your name, Kai, you don't even look up. I love it. Okay. So Kai is actually not here. But what we're going to do is we're going to talk about least squares. Hey, Kai. He's here now. Okay. Least squares. So I decided to do this backwards and give you an application and then go into the theory. Then we'll go back into the applications. But, least squares modeling is basically you need a mathematical model of data. That's it. I mean, the data, if you have data that's like y of x, right? Y equals f of x. Then, and that data is linear, right? So, which means basically that the coefficients that you care about in the data, they're all like, y is equal to b0 times f0 plus b1 times f1 plus b2 times f2, where b are the coefficients you're after and f are the functions of x, right? So it's a coefficient times a function of x, right? Then you can figure out what those b values are. As long as you have like more data than you have parameters. So if you want to get 3 parameters, you need like 5 data points, that type of thing. So a good example, of course, is the slope and intercept of the best fit line, right? You could calculate the bond strength and bond length of a diatomic molecule given its rotation and vibration spectrum. You get the rate constant and reaction orders of a chemical reaction and many other. So here's generally how that looks, right? The general form of the linear function is like this, right? Y is equal to B0 times F0 of X plus B1 F1 of X plus B2 times F2 of X plus da da da, right? So you can get a whole bunch of B values if they turn out to be useful. So so really what you really need is just Y data and X data, right? Or alternatively, you could have Y and F0 of X and Y and F1 of X and Y and F2 of X, right? So you don't actually even need to know the functions, so long as really the only thing you're doing is multiplying by B0 and B1 and B2. So I thought about this for a little while, and I decided that one way to make it appealing to you would be to pose a situation where you are developing an app, right? Because you're brilliant and you can do this shit. And your app is going to predict someone's GPA when they get out of college based on certain input data, like the number of hours per day they study, the number of work hours that they have, maybe their high school GPA, maybe what else matters in determining your GPA? What's something else that matters, Kai?
Something else that matters? What?
Yeah, something else that matters in determining and predicting your GPA when you get out of college.
When you get out of college or when you're in college?
You know, like let's say at every year in college, right?
Uh-huh.
At the end of the year, just to sort of put some parameters on it.
Oh, the number of units you're taking.
The number of units you're taking, exactly. Right, because if you take a huge number of units, you'll get a lower GPA, exactly.
Yes,
right?
exactly.
Cool. So those data can be the f of x data, right? And so what you can do is you can go through and take a big poll of people, right? Get a whole bunch of people and give them this poll, like how many hours do you study? How many hours do you work? What was your high school GPA? How many units are you taking? And what is your GPA, right? Your GPA will be Y, right? And then the number of hours you study will be F0. And then F1 will be the number of work hours that you have. And F2 will be the number of units that you're holding, right? And what you want to do is develop a function which is basically just this set of B values, B0, B1, and B2, right? Maybe B3, right? And once you know those B values, you can say, okay, tell me these things about yourself and I'll predict your GPA, right? You know, and it could work, right? Now, I'm not saying that there's necessarily a linear function that will work here, right? But I'm saying you could do this model and you could find the coefficients, B0, B1, and B2, that best match your predicted GPA to these input values of study time, et cetera, right? Does that make sense? You can make a predictive model. And by the way, can you guys hear me okay? Okay, good. Yeah, because I don't have my headset today and I don't know where it is. But so that's a case where you have just a bunch of data and you're going to assume it's linear, and you're going to get the coefficients that best match the acquired data to the input data, right? So so that process would involve polling a bunch of people for their y sub I given their x sub I, right? So you'll take a poll of all the undergraduates, or as many undergraduates at San Jose State as you can, and you can get the first person, his study habits, his work habits, his number of units he's taking, right? And you can get a bunch of those data pairs, right? The y and the F0, F1, and F2 of x, right? And the F0 of x, F1 of x, and F2 of x, these are the variables in a multivariate exercise. So you'll do multivariate linear least squares to those data and come up with a B0, B1, and B2 that best fit the model to the data. Does that make sense? Cool. So here's an example of this where you can take XY data, where the XY data are pressure and temperature. You can take a flask of stuff, and you can boil it, and you can measure the vapor pressure of this stuff, the P value, versus different functions of the temperature, right? So you can develop a P versus T data set, right? And it's just one number, one number, one number, one number, one number, one number. This is you vary the temperature, right? And then you can modify these data by taking the logarithm of the pressure. Then you can take F0, which is the inverse of the temperature, F1, which is the log of the temperature, and F2 here is simply the number 1, right? So F2 is going to be, well, if my model is log P is minus delta H over R times 1 over T plus A over R times the log of T plus a constant, right? Then for the constant C is simply the number 1. F1 is the log of T, and F0 is T to the minus 1. Hopefully that makes sense. So then when you do this least squares analysis, right, you'll get, you'll have all these transformed data, and when you do the linest, or however you do that, the B0 value that pops out of the model will be minus delta H over R, right? Delta H is the enthalpy of vaporization. B1 will be A over R, right? Because that B1 comes from the model. Delta H over R comes from the model. And C also comes from the model, right? So this is just another example of how you can take XY data and extract interesting parameters from it, right? So for example, people might be interested in the enthalpy of vaporization of a liquid. You know, that's a measure of the amount of heat that it will consume when it evaporates, right? And this A term is a nonlinearity in that model, right? Which this particular liquid may exhibit. And then B2 is a constant, which you need to model the log P versus the pressure versus temperature. Pressure versus temperature qualities of a liquid. Yeah. So, so this is the theory behind it all, right? What you need is to define a variable called chi-squared here, which is the badness of fit, right? I say it's badness because the larger it is, the worse the match between the data and the model. So hold on here. I have something to do this shit, but I lost it, so shame on me. Okay, I've got to do something else here, hold on. So, for example, we can take the least squares modeling of a line, right? And in that case, we'll have a set of data. Zero, zero, 1, 1, 5.
Dr. T, your camera's sideways.
Turn that camera. Hold on, I'm gonna fix it. There we go. There we go. 2, you know, maybe 5.1, 3, maybe 6.4, something like that, right? And we've got a point here, got a point here, and a point here, right? You say, well, what is the line that best fits these data, right? So the model is a line. That's a line. Hold on. The model is not a line. The model is a line with an N. If your model is a lime, then you're drinking and you need to stop drinking. I cannot believe you guys would drink in class. I think it's Kai's fault, though. Kai, have you been drinking? Okay, I'm just checking.
It is
Okay.
a Thursday.
I know, but it's actually my Friday.
Me too. That's why you're drinking.
I know. Well, I haven't actually started drinking. You know that? Oh, look, Kai's drinking something red. I don't know what that is.
It's nothing. It's soda.
Oh yeah, I think it's a margarita. But anyway, so the line is y equals m times x plus b, right? So there's two parameters, m and b, right? B is the intercept, and m is the slope. Right? So what we can do is we can ask ourselves, well, what about this data makes the fit good, right? So for example, I could say, well, what about that line there? Take this line, you know? This has got a slope and an intercept, right? And what makes this line a good or a bad fit for the data? And you could say, well, it misses the goddamn data points, right? You wouldn't have to say goddamn. You could just say it misses the data points. But I would say, okay, well, let's quantify that in a particular way here, right? We could say this is miss 1, there's miss 2, there's miss 3, and there's miss 4, right? And mathematically, miss 1 is equal to y1, or yeah, y1 minus y fit 1, right? This is y fit 1, right? Is this value right there. And this is y1 right there. And then we can add all these up. Right? We can add all these guys up, right? You can add this value, plus this value, plus this value, plus this value. Right, Kenya? Excellent. So there's a little bit of a problem with doing it this way, though, right? Well, first of all, we need a single number that represents the badness of fit, right? So we can just add all these up. We could call this number chi here. Not you, Chi, the other Chi. This would be chi 1, 2, 3, and 4, right? We could say, well, let's take the sum of those chi values, right? But what's the problem with that, Calvin? Does anybody know what the problem with that is?
If you had a negative and a positive value, they'd cancel out.
Exactamundo, right? So this miss is negative, this miss is positive, so y fit minus y1 will be negative, this guy will be positive, and you can get a 0 chi squared for a crappy fit. So we do what any self-respecting mathematician would do in this case, and we square the damn quantity. In which case, chi squared 1 is now positive, chi squared 4 is positive. What about chi 2? Chi 2 is positive or negative, Hikun?
Positive.
Exactly.
Oh yeah, the square is positive.
The square is always what, Kenya? I could hear you even though you were muted, and you said positive. And you're talking still, but I cannot hear you actually. Okay. All right. So chi squared is a positive value. And the larger chi squared, here, let's take a quiz. The larger chi-squared, the better the fit. The larger chi-squared, the worse the fit. Answer in the comments. And don't all copy. Aditya says B, 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 B. Good. Right, the larger chi-squared, the worse the fit. Exactly. So, you know how I like to think about this? I like to think of it like chi-squared is like a rubber band. And when the rubber bands are as small as they can be, okay, so you have immovable points, and here, 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 and here, right? Then you rubber band them to a stiff rod, and then you let the rubber bands relax. And then when the rubber bands have relaxed as much as they can, then you've minimized chi-squared, right? I don't know, it works for me. Does that make sense? Did anybody watch the debate? Holy shit.
Yeah, that was embarrassing.
Oh my God.
Talk about that.
It was I remember what CNN said. It was like a dumpster fire wrapped in something else, And then Dana Bash said, no, it was a shit show. She said, we're on cable. I can say shit. That was so funny. Anyway. See, I'm still apolitical. I'm just calling it a shit show. I didn't say whose shit show. Okay. So, yeah. How did your friend feel, Ivy? She was horrified. Yeah, right. It was like a bunch of second graders throwing spit wads at each other. But I got some insight onto this, right? I'm reading a book by it's this, yeah, you can cry a little bit, Yeah. Geez. But Trump actually believed this. He's in a weird situation, right? Part of it is that he believes these things, right? Because what he doesn't see is that Fox News is making a shit ton of money off of it, right? All they do, and he gets all of his opinions from Fox, all of them. He watches the news in the morning. There's this morning show that he watches with Steve Doocy and some couple of other guys. I don't even know their names, right? And he gets his information from them and all of their opinions and everything, and he forms his opinions. And they are super nice to him. He can never do wrong in their eyes, right? And by being nice to him, they get this audience, right? They get a certain segment of the audience, and they get paid for that, right? And these people are paid way like $20 million a year, more than any other real journalist, And what they do is they feed back to Trump what he wants to hear. And so he starts to believe it. And then the other person that he communicates is Sean Hannity. And Sean Hannity is like fucking Rasputin. He is the power behind the throne, I swear to God, because he gives Trump so many ideas. And then, and he believes him, right? That's one thing, right? Another thing is that he's a businessman. And he does not want the coronavirus to further tank his business. So that's why he's so against masks. He's so against shutting down and everything. He doesn't give a bleep about anything except his company's making money, right? Did Younger about his taxes? Oh yeah, I heard about him. Yeah. And his taxes, he pays like $750 or something. It's like, what? Oh my God. You know how much? That's less than, anyway. But you know, so, and then the third thing is that he's got a bunch of debt. And so he has to win, you know? His friggin' life depends on it. So he's just doing anything he can to win, you know?
Yeah, if he doesn't win, the Russians will kill him.
Right. There's a lot of
I'm
speculation.
only partially joking.
Right. I mean, who knows? Who knows? I mean, I'm getting a little bit speculative here, right? But he could be beholden to the Russians. Well, that was an interesting thing that the New York Times put out. He said there was no information about Russian debt. But I mean, it just seems like he sold this condo to this horrible Russian oligarch. And this guy was just like terrible guy for $50 million, right? Oh,
This sounds
God.
like a soap opera.
I know. It's friggin' reality TV here. It's just
They
a
should
little
make that into a show. Oh wait, The Apprentice.
right, exactly. Ah! Oh my God. What did he say about the fires? I didn't see that one, Kenya.
Oh, he basically said that the fires were because we don't clean up our forests and how we have a bunch of like dead stuff all over the place.
Oh, right. Yeah, right. We got to rake the friggin' forest. Come on. I mean, you know, in theory, maybe, but where does he get these ideas? Where does he get them? You know, that's the thing. Anyway. Yeah, the firefighters' faces. What did you see the firefighters just trying to preach? um, I didn't see the firefighters' faces after that. Were they in the audience there? Or? Anyway. Yeah. Anyway. So anyway, that's so hold on. So I'm going to get back to our previously scheduled programming here, and say, well, if you square these residuals, then you can with a single metric, you can optimize B and M, right? So there's a little bit of magic in getting them both done at the same time, right? But if you can just imagine that as you change B, let's say you have the slope correct. And as you change B, what you'll do is you'll go too low, just about right, too high, right? And chi-squared will go down, up, right? As you go through that transition. Does that make sense, Richard? So you can, by adjusting the B value and by following chi-squared as a function of B, what you'll see is that, oops, sorry, this is chi-squared versus B, right? That there will be an optimal value for B. Because chi-squared will, if chi-squared is too low, or I'm sorry, if B is too low, chi-squared will be high. And we'll come down to a minimum and then it will go back up. And this actually, the way we set it up, this is a parabola. Oops, this is a parabola, right? And so for a parabola, you can find the root, right? It's super easy. And the way you do it is you take like, you can take, you know, let's say that chi-squared versus B is, you know, well, you can take the derivative of chi-squared versus B, you know, whatever that function is, and set it equal to 0. You know, And then when this is equal to 0, then this thing will go through a minimum. By the way, if I have offended anybody, I'm really sorry. You know, I don't mean to like trash on anybody. I'm just get a little bit passionate about things sometimes. So just forgive me. You know, I love Donald Trump. I just don't think he should be our president. That's all. You know, that's all I'm saying. Robert, make me a gin and tonic. I need it. I need it in 35 minutes. Okay, excellent. That's my son.
I got some raspberries for your gin and tonic.
Ooh, very nice. Very nice. I like that. Okay, so so what if, will you pay our tuition if I'm offended? Oh God, I wish I could, guys. I'm just not that rich. Oh goodness, sorry, Adam. But I can't pay your tuition even if you were offended. So let's say that we have chi-squared versus b, right? But chi-squared is a function of two variables. It's a function of b and m, right? So I'm going to add a third dimension here. Make that third dimension m, right? So for every chi-squared is a function of m and b, right? The slope and the intercept. Yes, son/bartender. He just turned 21, so I'm exploiting that to the maximum effect. He's super excited about it, so he will make me drinks right now. So the effect is that there's a parabola of revolution in the MB plane. Yeah. So there's a combination for every point along this periphery here corresponds to a different point in the plane, you know? And there is a specific point where both B, M, and B are at the single unique minimum for the structure. And that single unique minimum is right here. This is B optimal, and this is M optimal. M mopped and bopped. And if you say mopped or bopped, I will give you an A. No one's willing to do it? Okay, I understand. Everyone has a certain degree of
Say
self-respect.
what? Mopped and bopped? What is that?
Okay, can you get an A? Who gets an A? Yes, mopped and bopped. Mopped and bopped are the M, the optimal slope, and the optimal intercept, right? Mopped and bopped are those values of M and B which match the data to the best fit line, right? Here's Y and there's X. Y is equal to mopped times X plus bopped. Sorry, my writing's not very good right now. So this is just two parameters, M and B, right? And the function of X is just X, right? So if you wanted to set this up in a least squares thing, you'd have y and x, right? 0, 1, 2, 3, 0.1, 2.4, 5.1, 6.7, like that, right? And you'd set it up such that, F0 is just x. And F1 is just the number 1. Then, and you'd have y sub I is equal to B0 times F0 plus B1 times 1, right? And B0 and B1 will be the parameters that you get out of the fit. And B0 will equal, and B1 will equal. And what will B1 and B0, B0 and B1. B0 will be which? Mopped or bopped? Oh, come on.
Mopped.
Mopped. Thank you. Mopped. And B1 will be mopped. Excellent. Okay. So, now, when I was saying earlier about this whole mess where we get a bunch of GPAs, and we get units and then hours studied and then hours worked, then what we can do is we can just say, well, we can get a bunch of data, 3.2, 7, 6, 12, and then 4.0, and then 6 units, 12 hours studying, 0 hours working. This we would just set up data like this, right? These will be the y sub I. These will be the F0 sub I, F1 sub I, F2 sub I. Right? We just poll a bunch of people, and we'll need to get at least 5 people to answer this poll, or maybe sorry, we need at least 6 people to answer the poll before we can get these coefficients, because we need 3 coefficients back. No, we just need 4 people, and then we can start developing coefficients. But the more the more data we have, the better the b values that we can get out, right? Okay. I'm sorry, my writing is just atrocious today. But if the GPA depends on the units, right? Will the value of B0 and assuming that, oh wait, no, I can't ask that. Okay. So let's say that the hours worked has a negative impact on GPA, right? If someone doesn't have a job, they can study and they will get a higher GPA, right? Then will the coefficient B2 be positive or negative? Okay, Ivy. Okay, it looks like Richard said negative positive. I'm not sure what that means. So let's see here. Let me just reframe this question again. This one, I'll kind of redraw it here. We have GPA as a function of units, hours, studying, and hours working. Right? We've got data here, right? And the model is going to be that GPA is equal to B0 times units plus B1 times hours studying plus B2 times hours working. Right? And let's just stipulate for now that the more you work, you lower your GPA, right? So given this, would B2 be positive or negative or zero? Richard, change your mind. Okay. The more you work, the lower your GPA, right? So there's something that you multiply by the hours working, which it's like it has the same units of GPA, right? So Dan says negative. May I ask Dan why?
Because when you increase the number of hours, your GPA goes down. So the answer, I guess, or when the equals is negative. So like the GPA goes down as a result.
Right, it's like you're saying the slope is negative there, right? Oops, sorry.
Yeah, I guess your constant would have to be like 4.0, right? Because then you start at 4.0 and go down.
Well, remember this is only one variable, right?
So.
and the model could have weird predictions. The model could say, oh, your GPA should be 7, right? What's to constrain it, right?
Yeah, that makes sense.
Yeah. And the model doesn't have those types of constraints in it, right? But if the hours of work negatively correlate to GPA, then B2 will be, who do I never call on? Leslie.
Yes.
Will the B2 value be positive, negative, or 0?
I don't know. I would think negative.
You are correct. Your intuition serves you. And we know that your intuition is more than 75% right, because when posed with a 50-50 chance, 75% of the time you get it wrong. So good job. So, I mean, everybody gets it wrong 75% of the time. So, so that is pretty much all I want to say about on this subject. So let me go back to the old PowerPointio here, and let's look at some of the baffling, mysterious mathematics here. Chi squared is equal to the sum over I of y sub I minus B0 F0 plus B1 F1 plus B2 F2, whole quantity squared, right? Does this make sense to you? Y1 minus B0 F1 plus B1 F1, B0 F0 sub 1 plus B1 F1 sub 1 plus B2 F2 sub 1, square it, add it to Y sub 2 minus B0 F0 sub 2 plus B1 F1 sub 2 plus B2 F2 sub 2, square it, add it up. You see, add up all these squared residuals, and that gives you chi-squared. I used a $2 word there, which is residuals, right? Okay, cool. So now, to find B0, B1, and F1 here, that is the trick. And in the language of partial derivatives, it is the partial derivative of chi-squared with respect to B0 that will get you B0, right? And that is the partial with respect to B0 of, here's the equivalent of chi-squared, right? You can set that equal to 0, right? The question is, how do you pull out B0, B1, and B2 here from this partial derivative? Well, the first thing you do is you apply the chain rule. And the chain rule for partial says that d by dx of f of g of x is equal to f prime of g of x times g prime of x, right? F prime of g of x, right, is just the derivative of the f function here, which is, we have to define f, right? So f is going to be this thing squared, right? So the derivative of f is going to be 2 times the function. Then getting into it, you take the d by db0. This is the g prime of x. So you take the derivative with respect to b0 of this term, right? And it turns out that despite the weirdness of a sum, you can just forget the sum. Say, oh, this is just f0. It's minus f0, actually, right? And you just have to sum it up, right? So f0 is always a number, right? F0 is just a bunch of numbers, right? So the partial of chi-squared with respect to b0 is 2 times the residual times f0. The 2 times the sum of the residuals times f0. And the trick then to finding b0 is setting this equal to 0 and solving for b0, right? Well, let's just stop here and we can reframe all of these guys in the following way. D chi-squared by db0 is this. And so for any of the b values, for b1 and b2, etc., all we're going to do is replace this term here with a corresponding function. One will be f1. That'll be f1. Then the other one will be f2. It'll be f2, right? And so if we just sort of drop the basically we're going to multiply this out, b0 f0 times f0, you know, and then we're going to cancel the 2's, right? And we got y0 times f0 is equal to b0 times f0 times f0 plus b1 times f1 times f0 plus b2 times f2 times f0, right? That's this term times this plus this term times this plus this term times this, right? And one way this simplifies is the sum over I of y sub I is just a number. The sum over I of f0 sub I is just a number. Number. B0 is an unknown, B1 is an unknown, and B2 is an unknown, right? Then you go from finding B0 to finding B1 to finding B2 just by incrementing these values. Does that make sense? Sort of, more or less? Kenya says yes. This is the second time Kenya's heard this. Second time Calvin's heard this. But the first time I taught it, you didn't need to know it. I was just demoing it, right? Now I'd kind of like for you to remember it a little bit more than that. You don't have to be able to derive it de novo, right? But I'd like for you to get the gist just a little bit better than we did in Chem 101. Because this, after all, is Chem 250, right? We're kind of going up a level, yeah? So, Luke, here is what this looks like in matrix math, right? We've got YF, YF, YF. These sums. This matrix of 3 values here is equal to the Y matrix. There's 9 values here and 3 values here, right? And in matrix math, this is just Y equals X times B, right? Here's Y, here's X, here's B, right? And when you multiply a square matrix by a 1-column matrix, you just get B0 times this plus B1 times that plus B2 times that, right? So this all works, right? So the way to find the B values is to find a way to invert this matrix, right? So the inverse of a matrix, I think this is probably wrong. This is y times x to the minus 1 times x to the minus 1 times b, right? And I got the order of these wrong when I first did it, so you probably can't plug them in just like this. I'll have to fix this, I will. But the idea is that if you can find a set of 9 values, which when you multiply them in matrix math, you get the identity matrix, which is 1, 1, 1, 0, 0, 0, 0, 0, 0. Where on the diagonal, they're all 1, and off diagonal, they're all 0. Then you can solve this problem. And all you have to do is multiply y by that inverse matrix, and that will give you b. So x to the minus 1 times y is equal to b. And that's where those 3 numbers should jump out. So to wrap up today, I'm going to take us back to Excel, back to the same old misery that we had last time. And let's take a look at what this looks like. Oops. So let's see here. Let me change a couple of things around here. So this is toluene. I'm going to change this from toluene to our model for toluene. All right. Okay. First of all, let me connect this. Sorry, before I even do that, let me connect this problem to the one that we just did with functions, right? So what we're trying to do is we're trying to model a spectrum, right? And so The spectrum that we're trying to model is in the blue here. It's this blue line, right? And what we're saying is that this blue line ought to be the sum of the gray line times some constant plus the yellow line times some constant plus the orange line times some constant. And what we want to know is what those three constants are. Right? So the mixture of acetone, toluene, and ethyl acetate, the mixture of these three pure components, its spectrum should equal the mixture of acetone times the coefficient plus, sorry, I think I misspoke there. The spectrum of the mixture should equal the spectrum of acetone times the coefficient plus the spectrum of toluene times the coefficient plus the spectrum of ethyl acetate times the coefficient. So what do I mean by a spectrum times a constant? Well, let's take a look at that. Oops. Show here it is. So here's so what we can do here. I created some spin bars, and the blue line in this spectrum is the mixture, right? And the red line is a model sum, which is equal to 0.59 times the acetone spectrum plus 0.008 times the toluene spectrum plus 0.36 times the ethyl acetate spectrum, right? And what that means is that, let's say I make the acetone spectrum super huge, right? Right? So this spectrum, the red spectrum, is looking more and more like just the spectrum of pure acetone with a little bit of ethyl acetate, you know? Right? Does that make sense, everybody? Can I get a question maybe for what this button does? I'll send this spreadsheet out as soon as it's ready for prime time. There's just a couple of things I'd like to sort of get right. So Kenya says yes. Dan, does this make sense to you? Emerge from the cloud.
Yes, it does.
Okay. So can you explain to Pi what it means to multiply a spectrum by a constant?
I guess you're just changing the contribution of that spectrum, because when you have overlapping spectrums, there's if they're all equal, they'll have the same peaks, but if you have them at unequal quantities, like you can have them 1 to 1 to 1, right? Or you could have them like 1 to any ratio of them will change the peak heights of each spectrum. So that's what that little bar does.
I like it. Did that make sense, Richard? Not a bit. I'm just kidding.
I did have a question though. So this works if you have all the spectrums for known pure compounds, and you could have any number of compounds in some mixture.
Right.
But if you have a known compound, let's say ethyl acetate, and then you have some solvent you don't have a spectrum for, this will not work.
Right, it won't work. However, there's a funny thing that happens on the way to the popsicle stand here, which is that if you just have one unknown, right, you can Model T all your knowns, and it will get them pretty much right. then when you take the difference between the model and the spectrum, that difference will be the upside down of the unknown component.
So you'd be able to even get the spectrum of that and maybe
Right.
by it.
Right. You won't know what it is, you won't know how much, but you'll be able to get its spectrum. You know, pretty close anyway. Ikun, how's it going? Okay, good. So I take it that in Korea, this means okay, right?
Oh, yeah, I think so. Maybe. I don't know.
Right. Well, I mean, when I was in Colombia, I went there as a high schooler, and I learned that that is very rude in Colombia.
Oh, yeah, I heard that from my Colombian friend too.
Really? No kidding.
Yeah.
Oh my gosh. Oh my gosh. Yeah. So you have to be careful, right?
Yeah.
I mean, I don't care. I mean, you can do whatever you want, but it's just kind of interesting, right? Because like there's this, right? That's the peace sign, right? Peace or victory, I think. It means victory in England, right? But this means something very different. Actually, they usually go like this. And this literally means that I have the fingers that I need to shoot my longbow and kill you. Right? Because back when the English and the French used to be perpetually at war, they didn't know what to do. They were sort of like not really that serious about things, which is a good thing. And so what they would do is instead of like killing the prisoners or making them slaves or whatever, they would just chop off their fingers. So if you don't have these two fingers, you cannot shoot a longbow, you know? And so that was what that meant. The English, they would go like this to the French and say, ah, I've got my fingers, dude. Right? So that will be on the exam. And that is insultonomy. Oscopy? Insultoscopy? Insultometry? Insultometry. Insultometry. So basically what I'm saying here is that you can take this blue spectrum and match it to the red one by tweaking these three amounts, you know? When you do this and you start getting it closer to correct, then chi-squared will start to come down, right? Right? See, now chi-squared, it came way down, right? Now I'm about 70% acetone here, right? I'm going to go too low. Oops, that's not too low yet. Chi-squared still came down, right? But now as I keep going lower, chi-squared starts to go up again, right? Can you guys see that? Does that make sense? Cool, great. So this is your learning for least squares for this day, this first day of October, 2020. Yeah? Isn't that a sweet sound? You've learned everything I'm going to teach you. Now, I've been challenged to give you both review materials and a date for our midterm. And I am completely unprepared to do either of those things. Exam is how many fingers to shoot a bow. I love it. 2 fingers. But so I'm not prepared to do that right in the second, but I will get to it. And then we'll have some fun. and we'll go do some Excel. And I've just been not ready for y'all. So sorry, but hopefully we're learning stuff, and I won't give you any homework yet because I'm not ready.
Wait, are we gonna have an Excel sheet for our exam?
I have
Is that what
not
you mean?
decided yet, have I? I could do anything. I could make you wash my car, but then I might get in trouble with the dean, so I'm not going to do that. For an A, yes, for an A. You wash my car, you get an A. You won't tell. You can have an archery exam. I like that. That's cool.
But you said if we said mopped and bopped, you would give us an A.
Yeah, not in the course, just in the mopped and bopped exercise. I didn't say that at the time, but you have to assume that I'm not going to give away all of my power at this early date in the semester. And yes, I'm a lying sack of beep. Hi, everyone. But I could. Yes, I could, but I won't. Da, da, da. I'm a mean guy. Okay, so with that being said, I think we've done enough for today. And thank you for your attention. And I will see you again on Tuesday. And by that time, I'll have some better focus on exams and stuff like that. And because you guys don't have enough review materials, we're just all over the place. But I promise to get them to you. Yes. And peace to everyone, but not this. Excellent. Bye-bye. Let's see here. More.